Hello, this is an introduction to Docker. This is similar to presentations that I give at various web development consultancies to help bring teams up to speed on what Docker is, a little bit of its history, and how it can be used to make their work more effective, and sort of the overview of modern DevOps. Well, let's get started. So first off, about these slides, they are available at GitHub. You can clone them to get the code and follow along. There's also example Docker files, Docker Compose files, and a few other things that we'll be going over. Not all the content is in the slides. We will be jumping back and forth between the console quite a bit and trying things out. But there it is. Away we go. So first off, why containers? When in the beginning there was just hardware, we had our bare metal machines and we configured them to run multiple applications. But as hardware got larger, a single piece of hardware was really too much to run an application, or at least most of the applications that people run. We do run large sites still that require many pieces of hardware, but your average server that has 16, 32, 64 gigabytes of RAM is a lot larger than the average web project needs. So instead of sharing hardware, we moved to VMs, virtual machines. And then each virtual machine could have its own environment. It could be dedicated to a specific purpose. And we can have our generic 4 gigabyte workhorse application servers. The problem here is that you have to decide everything up front, and not just when you start the app, but when you build your environment, when you build your machines. So if you guess that your next web project is going to need 4 gigabytes of RAM, and you give it 4 gigabytes of RAM, and it turns out all it needs is half a gigabyte, well, you wasted some. And if it turns out you needed 12 gigabytes, shucks, gonna have to throw away that VM and start again. So containers are actually an older technology than virtualization, than VMs. They just didn't catch on in the mainstream when they originated. Containers let us do resource allocation at runtime and even variable at runtime. So you can definitely tell a container that it can only use 4 gigabytes of RAM, but it doesn't have to use that much. If the app inside of it is only using 512, 128, 30 megabytes of RAM, then that's all the container uses. The same with disk, network, CPU. While you can apply constraints and you can adjust those constraints while the application is running, it doesn't have to use anything more than what it is actually needing right now. This allows for much denser utilization of existing hardware. Another thing is that VMs take much longer to start up. Even a pretty fast VM startup is probably going to take around 30 seconds. If this is provisioning another host on a cloud service, you're probably looking at a few minutes, and then you need to configure it afterwards. Containers start up within milliseconds. They are basically just starting whatever single process your application is. They add no appreciable amount of overhead to starting your app. Another thing is containers. Another thing for containers is performance. Google runs their entire infrastructure within containers. Containers are extremely lightweight. There's some measurements that would, depending on your application, the performance overhead is likely to be in the noise. There have been some reports because of the different paths in the Linux the security and permission section of the Linux kernel, that your application might actually run ever so slightly faster in a container than outside of it. So you can run your containers on bare metal, or even if you have to layer your containers onto a VM, at least they will not add any additional overhead. There is one caveat, and that is that if you are running your containers using Docker in a dev environment on, say, using Docker for Mac or Docker for Windows, there are some performance problems, primarily around shared disk access with the host. That's getting better rapidly. At the beginning of this year, I'd guess that the Docker for Mac container drivers were maybe 30 times slower than direct disk access. Now, for most of the apps that I'm working on, it's about 3 times slower. They're getting better. Give them another 6 months or a year, and that will go away. And even as it is now, it may not be a problem, and there's a few ways to work around it. Personally, I run on my Mac a Parallels VM and then use that to host my local deving containers. Parallels has a nice file system sharing driver. Everything just works and performance stays up. I don't really notice it deving inside the container or deving outside. I'm looking forward to Docker for Mac because it is so nicely integrated and it's completely free and it just works when they'll get it just a little bit faster. So far I have mentioned Docker, but most everything I've been saying is about containers, and containers does not exactly equal Docker. Docker is more than containers. Docker provides an image spec. That image spec is also beginning to go through an RFC process so that there are alternative implementations so that it is open. Docker provides a layered file system so that we have control and can reuse layers. We'll get to more about that in a bit. It also gives us software-defined networking, then of course containers, and lots of tooling and ecosystem services support everything you need around containers to make your use of them very efficient. So there are alternative implementations. One that you may have heard of is RKT or Rocket. This has been done by the CoreOS guys, and their primary focus is on improving Docker security with their own alternative implementation. In general, their things are compatible, and Docker is picking up things as it can from their improved security standpoint. Another containerization implementation is Solaris Zones. This has been around for quite a while, more than a decade, and Solaris Zones have the benefit of being very secure. Currently, with Linux containers, Docker containers, it is plenty for isolation between your own apps, but you do not want to run hostile code in a container on a machine that has other containers. You don't want to trust Docker to contain hostile code. There's some things around the Linux kernel and networking that it will probably always be possible to interfere to some degree with other containers on the host. So it's fine for isolation. It's not really a security mechanism. Solaris Zones, however, on the other hand, are robust enough to act as a security mechanism. BSD, the Berkeley Science Distributions of Unix, do have a Docker port underway. Last I heard that you could get many containers to run directly on BSD. Illumos offers an alternative Linux container and Docker implementation, which leverages some of the tech. Illumos is a descendant from Solaris. It's an open Unix-like operating system. They have one of the Illumos distributions is SmartOS, and the SmartOS guys have a very nice Docker solution which allows us to have Solaris Zone security, but an entirely Docker compatible runtime. So you treat the machine as a Docker host, and everything just works, and security comes along too. A great solution. There are also other possible future implementations that we've heard rumors of. VMware's apparently working on one where we can run containers directly under a hypervisor, no Linux kernel or VM in there anywhere. There's also been some news that Microsoft might be working on something similar. So lots of excitement around containers. All right, let's get down to Docker. So the things you'll need at first are the Docker engine and the Docker command line. Originally, I think to simplify the mental model of it, they are bundled as the same binary and often are referred to as the same thing. But I find it useful to separate early on which one's which. So the Docker engine is the daemon that runs on your machine, and that starts, stops, manages containers, the layered file system, networking. And the Docker CLI is the same binary that you just run on the command line and send commands to the daemon as its command and control. So Docker is internally a client-server architecture, and this comes in very handy a little later on. So the first thing we're going to start with is Docker files and the Docker registry. Docker files are what allows you to create a Docker image. When you start off with a container, you don't have any files within that container. It's on a host. There's the Linux binary API. You could start a program if you had one in your file system, but as you start with just a blank container, there are no files within that container. Docker files are what lets you create that initial file system, not disk level file system, but arrangement of files. And then the registry is GitHub for Docker. It is a place where you can share images, both privately with other members of your team or publicly with the rest of the Docker ecosystem at large. So using a Docker file or pulling a pre-built image from the registry, we can have different operating systems inside our container. Well, different Linux distributions. So say your app, you're used to Ubuntu, you'd like to run on Ubuntu. Well, we can go over to the Docker registry, and here's the Ubuntu repository. We can decide we're going to base our images off of Ubuntu 12, 14, 16, 16.10. Really just pick whichever version we want. In our Docker file, we'll say that we're building from, and then specify Ubuntu 16.10, and then the file system, the files that will appear in our image are those of a base Ubuntu 16.4 system. We're not limited to just Ubuntu. There's CentOS, Debian. On the smaller, lighter side, there's Alpine and BusyBox, Alpine is a very small, circa 7 megabyte Linux distribution, and BusyBox is even smaller. So whatever Linux distro you like to build your packages from, you can. There are others up on the registry, and you can always add your own. One point of note is that all of these are official repositories. This means that the Docker files, the builds, are maintained by docker.io, the company. So if you trust Docker and that you're running the Docker daemon, the Docker client, you can also trust them to build you trustworthy, reliable base images for the OSs. But we don't have to start at the Docker, the Linux distribution layer. We can start with an application stack. We can start with one that's just a language stack. So if you're working in PHP, and maybe you would like to use PHP 7, and it doesn't happen to be in your distributions package manager yet, well, just pull the Docker image. They build for 7, 5.6, everything that's current. They tend to stay very current, and there's a bunch of different flavors here. So we can pick if we want a nice light Alpine image. Maybe we only want the command line version of PHP. Maybe we want it bundled with an Apache web server, or perhaps just FPM if we're going to run under Nginx. Sort of whatever you want, it's already built and they're waiting for you in general. There's ones for Node.js, PostgreSQL, etc., and anything you want, pretty much, and you can always build your own. There's also, you don't have to start with an application or a language level image. If you use PHP and Apache and Laravel and PHP Compose, or the Node.js mean stack, you can go and find images that have all that set up and ready to go. You just pull them down and build off of them. A side note, while you're building your own images, so you specify which image you're going to start from with the from command and a Docker file, and we'll get to the structure and making your own Docker files in a few minutes. There is, however, a special minimal image called Scratch, and that is the blank image, since all Docker files require having a from line. Saying from scratch just means that you are starting from that blank slate. This is ideal if you want to build your own Linux distribution. You don't need anyone else's files in there. You just need the blank starting point, and then you can add all the files that come along with your distribution. That is also something that languages that can produce static, standalone, small binaries sometimes use. Some images written for the Golang may use just from scratch, add in your binary, run it. That's a little bit more extreme than most people will probably use. I find that the Alpine-based images are very small. A Node.js Alpine image weighs in around 30 megabytes. If you want to cut out NPM, you can maybe get that down to 16. So very light. He's quick to pull down from a server, move up to another host. It's just handy to keep them light and nimble. All right, so we're going to begin building a Docker file, and one of the first things you need to know is about the Docker file context. Usually, you're going to place the Docker file in a directory, and the directory that contains the Docker file and all subdirectories are what creates the Docker file context. Now, in your Docker file, you can add anything from that context into your image that you will build using that Docker file. Here is partially where Dockerfile's client-server model comes in. The Docker command line, when you say Docker build and give it a name and give it a location, is what you're going to use to build your Docker file into an image. And the first thing it's going to do is it's going to upload everything in that context to the Docker engine, whether that is something locally on your host or Docker engine you've connected to remotely. And that's where your actual build process is going to happen. So all those files in the context don't have to end up in your image. They are all available for you to say, add to my image. Let's skip that and come back. All right, image inheritance, we've already mentioned. You'll say as the first line in your Docker file, from, and then another image name. That image name is where we're going to start our Docker file, our base from. So a few things to note is that each command in the Docker file is run as it creates a separate layer in the file system, in a layered file system that Docker uses, and they're cached. So if you have two images that share layers, say you have your application and your database that runs with it, you want to run them on the same host, and you're going to build them both from Ubuntu 16.10. That means you only need to pull down Ubuntu 16.10 once. Both images will use the layers that create that, and then only diverge when one is going to install your database and one is going to install your application. So by using image sharing, you can cut down on any network transfer size, storage space on disk, and just make things more efficient. It's also possible to have images which are context-free. So if you simply pipe your Docker file to the Docker build command, then the image has no context. There's nothing around it that you can add to your image. And this doesn't cut down on the image itself size, but it could cut down on the time it takes to get that Docker image built. There's also equivalent to a gitignore file, there's also a docker ignore file, and there you can list paths, regular expressions, or file globs that you do not want to include in the context. So when you're uploading when you're building your image and you're uploading it to the engine. So perhaps you had a large node modules directory and you don't want to include that. You want to pull down fresh dependencies. When you build the image, you can just add node modules to your .docker ignore. Everything works. One intent of the Docker files is that they be entirely portable. They build on my machine, they build on your machine, and they can build on the registry or Docker Hub. It is, of course, possible to make an image that won't fit within that constraints. If you add commands to pull in files from URLs that only resolve within your local network, then the registry can't help you. Someone else can't, someone else on any old machine won't be able to build your image. But ideally, your images are entirely portable, and as a convenience, the Docker registry can build them for you. So it's very easy to connect the Docker registry to GitHub or Bitbucket, where you're keeping your Docker files, and then each time you make updates to your Docker files, you'll just automatically have nice, fresh images on the registry waiting for you to pull down and run. So we won't cover all of the Dockerfile commands. These are just the ones that I think you'll find are most important. We'll go to the command line in a few minutes and make our own file. But there's going to be from, which is which image we're coming from. The maintainer is just informational. Usually put in your name and email address so we know who made this Docker file. Run is where you say run, and then you can use shell scripts using your distributions package manager. And each statement in each run block creates a new layer on the file system, as does add and copy, workdir, command, etc. The add and copy commands, it is idiomatic to prefer copy. However, add is a little older and has a few more capabilities, such as if you use add to add a file to your image that is a tar archive, it will automatically decompress and untar those files for you. That's not intuitive, so it's easier to use copy unless you're really needing the additional power of add, which some case that you might want that is if you don't have any untar or uncompressed commands in your image, because it's a very bare bones image or you're starting from scratch and you need the Docker engine to give you just a little bit more help to get bootstrapped. Workdir creates and moves the rest of the Docker, creates a working directory. It can create or move you to a working directory in the image and sets that as the working directory for the following commands in the Docker file. Command is a way to give this Docker file a default command when it's run. It's entirely optional. It's often easier to set these at runtime, but it can be handy to have an image just have a default. If I just run it, it knows what command it needs. Environment is for setting environment variables in the image and the container when it starts. Okay, here's the formal note about add and copy. Add is still needed. It can't be depreciated, but we're encouraged to use copy unless you really need add's functionality. And there's a link there to the best practices. All right, we'll go a little bit further and then jump to that Docker file. So one thing we need to know is Docker is to a great degree like Git. One thing that we need to know is what is a repository in Docker terms. So repository is repository name. Usually that's your organization name / image name, : tag. The tag is optional. However, if no tag is specified, the implied tag is latest. It can be a little unintuitive, but if you build an image, don't give it a tag, you automatically have a tag of latest. And that will show up in some commands and not in others. You can specify that most recent one by saying tag latest. Let's go. All right, we'll start here on the Docker command line. So Docker pull. Here I'm going to say that Alpine image, and this one happens to be an official repository, so it doesn't have that repository prefix. It's just Alpine, and then the tag is 3.4. Let's go ahead and do that. So switching to the command line. It's a little larger. Docker pull Alpine. And actually, I need to tell it mine. Well, let's get this set up. So here, we'll get to some of these commands later, but using Docker machine, I'm starting up my local VM for my dev work. And then up above, as soon as it gets started, we are just going to tell my local Docker client to talk to that server. Give that a few minutes to start and go back to the slides. So Docker pull, just like Git, we have pull to pull down fresh images. In Git, you're pulling fresh code. In Docker, we're pulling fresh images from the registry. We also have Docker commit. So the better way to build your images is using a Docker file, but you can build them manually. This is a great workaround if the application you're containerizing has maybe a setup procedure that's difficult to automate, or that uses a GUI and there's just extremely difficult to handle, extremely difficult to automate, or there just doesn't seem to be a way to automate it. You can pull the image, run steps in it manually, do whatever you want to make changes to that file system, then commit those changes, and you can push it back up to Docker push your repository name, push it back up to the registry. Another side note while we're here is that while Docker runs an official registry and its prices for private images for private repositories is quite low, they're not the only ones that run it. Google runs one, AWS runs one, I believe Joyent and Rackspace may be running one. It's also, the registry is a free open application, same as the rest of Docker, and it also runs containerized. So you can just pull down the container that is the registry, run it on AWS EC2, connect it to S3 for storage, and voila, you have your own private registry. Let's go back. My VM should be started. All right. Yep. See, VMs take a lot longer than containers. All right, and we are setting my local machine. All right, I'm going to Docker pull Alpine 3.4. Now, because I have already used Alpine 3.4, that image is in my local Docker cache. I can see my local images with Docker image. So we have Postgres, Alpine, various images that I've been working on, one for PHP, there's Nginx. In each of these, we can see over here on the right, there's a file system size. Because they share layers, your entire disk usage will be less than the sum of all these. But if any of those images were to simply be a standalone one on one host, it would take that much size uncompressed. We do have efficient network transfer, so we're not sending this many bytes over the network. Everything is compressed before it is sent to the registry or pulled down. All right. And just like Git, we have, besides Docker pull, push, pull, commit, we also have Docker tag, same ways you'd use Git tag to give a more descriptive name to a particular commit. You can give a tag and more descriptive name to a particular image layer, which is usually that image layer and all the images, all the layers previous to it. So we can do something crazy. Let's run. So, and as you can see, that was near instantaneous. that was much shorter than how long it took to start up my virtual machine. So here, what I did is docker run, get me a terminal running shell inside Alpine Linux 3.4. All right, so my machine happens to be Mac, but as we can see, this is a Linux file system. I'm in Linux, and I'm running Alpine Linux. Welcome to Alpine Linux 3.4. Alrighty, so inside a container where you can do crazy stuff and not hurt our host. So if there's any sysadmins out there, don't twitch too hard. Yes, I'm going to blast root and see what happens. Okay, so we deleted everything except a few files that are busy and we can't seem to delete. What do we got? Nothing. You can no longer list files because ls is gone and there's just sort of nothing left. If we want, we can see this image. So again, this first bit is just to tell my freshly allocated shell that which Docker engine I'm talking to. So Docker PS shows me the one that I'm running. We started about a minute ago. It's been up about a minute. It has an ID. We know which image this came from. And we can Docker tag that image. So Docker tag. Now, this image is one I was already called bad idea, and we're going to make it bad idea v3. Usually a bad idea to delete every file in your image. So it's Docker tag the ID or existing image name, and then the new tag we're applying. So we have pull, push, commit, and tag. Let's dig into what some Docker files look like. So along with the slides, there is examples. We're going to go into the examples directory and look at the sample app and then a Docker file. This is a very simple Docker file that containerizes a Node.js app. So first off, we have from mhart Alpine Node. mhart Alpine Node is a minimal Node.js image built by user mhart. I trust him. I worked with his images for quite a while. It is, however, a better practice to build your own images for your production app. So you build your own base images for your own apps. There is, of course, always the problem that even while this is a public image, mhart seems trustworthy. We've built stuff from him for a long time. Who knows if his account gets compromised and someone puts some malicious binary into that image. So it's a good practice, not necessarily required for dev, but before you put containers into production, have your own images. Make a clone of the Docker file for mhart Alpine Node, make it your own, and work from there. So the next line, maintainer, we're going to put my name, my email address. It's nice to know who built this image, who understands what's going on. We're going to make one layer, npm install -g global install this package, something that I know I'm going to want for this image. I'm going to make the work directory /app, add everything from the context. This is possibly a little non-intuitive. I grew up with ads, so I tend to still have it in my Docker files. Copy would work fine here as well. It'd be more idiomatic. Right here, we're saying that first dot is everything on the outside, and add everything. So add everything on the outside to right here. So that puts everything in my Docker files context and dumps it in /app inside the image. And then I'm going to run npm install. npm is the Node.js package manager. It is going to look at my list of packages that I want for this application and install them. Okay, so let's look what the outside of that folder looks like. So here I have a Docker ignore file, which is ignoring the node modules directory. Node modules is where the npm package manager stores all of its dependencies. So I want, every time I build this image, to pull fresh dependencies that match exactly what I specified in my package.json. And I'm going to, that's the last command in our install script. And I want just to install them all into the image. There's a Docker file, which we have open over here, and we'll get to Docker Compose in a bit. And index.js is my very simple application. All right. So let's build a Docker image. Docker build -t. Okay, so Docker build is the command we're going to use to build images. -t is how we're going to specify its name. So this one is going to be called demo sample app. Actually, let's do there. Okay, so, and this will build. Or it should build. Well, let's find out why it didn't. That's okay. So so this will build, and there it is. It's going through all the steps, and we'll look more closely at that in just a second. Let's go back up to the top and have a closer look at it. Okay. So here you can see that I'm claiming a global namespace of demo. The Docker engine doesn't care what repository name you use. However, if someone else on the registry already has an organization named demo, I won't be able to push this image unless I have permissions on that registry for that name. You may run your own registry, either locally or within your network for your organization. So it's not like domain names that someone else can take the name, because you can run a registry local. But those names are global within the scope of a single registry. So I can have whatever I want locally, but before I can push it, I need to authenticate to the registry I'm talking to, and then I need to have rights to that repository. Basically, pretty straightforward, same thing as like GitHub would. And if you ran GitHub Enterprise locally, the same thing, then you can have whatever name you want, but still it's nice not to collide with GitHub public. So here we have a repository name of demo, the image name is sample app, and we're going to give it a tag of v1, and then because I am in the sample app directory, the path is simply dot right here. So the first thing it does is it sends the build context to the Docker daemon. Our build context is quite small without that node modules directory, a couple kilobytes. That's being uploaded to wherever I'm running the Docker daemon, which for this here is locally on my machine on another VM. It could be on one of your servers running the Docker engine if you wanted. All right, so each step goes along. Each step is a layer from Alpine node. Maintainer gets its own layer. Installing nodemon gets its own layer, and that has npm spits this out a bit of information. Let's pull stuff down. That's an npm warning there. We have another layer, app. We're adding our files all the way down at the end. We're done. Okay. Now, if you think back a few minutes, you saw that took just a little while to run. Not long, because we don't have many dependencies, but it did take an appreciable amount of time. I ran it again, basically no time at all, because it sees the Docker file has not been modified, so we can reuse that layer, and we build the entire thing basically instantaneously. The layered file system, besides sharing files, besides sharing layers to optimize your on-disk image sizes, this optimizes building, so you only need to build the steps that have changed and any steps after them in the Docker file. I've used this frequently when I have larger apps that need to be containerized. Pretty much all mainstream package managers are not entirely deterministic in their behavior. My worst problems have actually been with Python's package manager pip, but pip, npm, composer, any tool, Maven, Lean, whatever, they're not generally entirely deterministic, so that each time you build an image, you might get different versions of dependencies or different versions of dependencies. Sometimes you need to get exactly a specific one, or you need to have a known good build. It's nice to break each one of your individual package installation steps into a separate layer, or maybe you're downloading and compile some stuff. That way, that if you're get 90% through the process and something breaks, you can start again at that 90% mark rather than starting again all the way at the beginning. Of course, you can delete the previous image layers or modify the Docker Compose file and start again, do everything fresh. But it gives us a great deal more control. You can also go in here and see which files have been added to the file system at each layer. So if you're exploring a new package, some new project, and you want to see what exactly is this going to do to my machine, it is possible to see the diff at each layer. What happened here? Very handy. All right, so we have a simple image file, and we're able to build it, and we can see it. We list out so there are Docker images, list out the images this host knows about. I'm grepping for the demo one, so we see demo sample app v1. It's not a SHA, but it's ID, and it was built 5 minutes ago, and the total size was 65.17 megabytes. So that's Alpine Linux, npm, Node.js, this app, our NodeMon dependency, the works. Let's actually go inside that. Let's run that image. So that image does have our app in it. We'll do demo. Okay, so here we're inside the image we just built. The work directory is default of where we'll enter at when we say Docker run. If we do an ls, we have our Docker file, Docker Compose file, which we could exclude. We don't really need them in the running app, but hey, they're small. We have index.js, which is our app, in this case, package.json, which is its configuration. Yeah, its dependencies. Node modules has all of our dependencies in it. So we do have here it's a full Linux file system. It is, as far as we can tell, on Alpine, not on my Mac. We can see everything that we have in here, and so those are all of our dependencies. Everything's here. It's built. Okay, let's exit back out. Another point that would be very useful is that layers are immutable, which is what makes them shareable. But that's also, we can start many applications from an image, and any changes that those containers make are made to a layer on top of the image. So it is not possible to corrupt. It's not possible while using Docker tools. Those images are stored somewhere on disk. Again, you can go find them and flip bits. But using Docker tools, you're not going to corrupt your image, your base layer, where you're starting your containers from. And you can start as many containers as you want from that image. So we just started that one to demonstrate. So here we're in app. So we removed our app. close too many windows. All right, let's run another container from that same image, and index.js is still there. It is immutable. All right. So we've gotten as far as we know what the registry is, we know what containers are, we know what a Docker file is, we know what a Docker image is, we know why we need them. We can add our application into image so that it's available to run. We can use basic command lines, and Docker has a great built-in help. So there's Docker help with all the commands. We can use Docker run. So this Docker help run. And there lists all the different things that we can set for a Docker run. We can use Docker run to run our images. And now it's time to address the things that we can only do, not at image build time, but at container runtime. So things such as setting the configuration for this run, software-defined networking, just sort of the rest of it. And a point here, just a pause before we go on, the 12-factor app pattern. If you are going to do any ops at all, please go to 12factor.net and have a look over the 12-factor app patterns. It's quite short. There are 12 of them. Each one has their own page. Let's look at config. So it really is quite short. The 12-factor patterns are not in any way Docker specific. They're older than Docker. They're like 10 years old. They are tried and true DevOps. This works better. They have a pretty good brief introduction of what the thing is. So say what you should do to your code base. One code base, track and revision control, many deployments. Dependencies, explicitly declare and isolate dependencies. Config, store config in the environment, so in environment variables. Backing services, treat backing services as attached resources. And each page details in greater depth what these principles, this pattern means, different ways of implementing it, and sometimes why this is important. So this is not Docker specific or container specific, but containers do make many of these things easier. And if you do these things, you will make your operations life much easier. They are tried and true. They work well. So let's see how we're running on time for the presentation. All right, doing pretty good. All right, 12-factor app. So we're going to use some of the 12-factor app patterns. Docker is very much aware of them. It does gently guide you towards that way. Specifically, we're going to look at configuration through environment variables, as you have. So actually, let's step back a little bit. So we can build our images. We add our images. We add our applications to our images, and then we have an immutable image which we can start many running containers from. And that is the thing we are going to deploy to production. Now, currently, you are probably building your application. Well, hopefully, you will have a continuous integration, continuous testing set up, and you are building your app somewhere, and then you are testing it, and then you are promoting it through test, beta, staging, production, however your configuration is set up. Currently, you are possibly rebuilding that app. You do a build for test, and maybe you're doing a build for beta or staging, and then you're doing a build for production. You may be adding configuration in there, so you may be intentionally making your builds not byte for byte identical. So you're not actually testing the thing you're going to deploy. That is a little scary. But even if you're not intentionally making them different, you could be pulling slightly different dependencies. So maybe there's a dependency of one of your dependencies which you got the right one in test and it worked fine, and then you deployed into prod and the world blows up. So one thing that Docker makes easier is that you can build your image with it. Build your image. It has all your dependencies. It has everything in it, and then it is the artifact. That Docker image is the artifact that you run through your tests, through your continuous integration system, and it is the artifact that goes out and gets deployed. So you know that byte for byte, the thing you tested is the thing you are running in production. And you're not installing dependencies in production and somebody removed leftpad and the world blew up. If you don't catch the reference, leftpad was a very small library in the Node package manager that many other libraries depended on, and one day somebody deleted it and many things broke. If you're using a Docker images throughout your process, you know that you have a byte for byte, what you tested is what you deploy, and they are your bytes. You actually have that copy, and you can put up to your servers. It also helps when you're scaling to mini servers. You know that if you have 24 application servers, they're all running your image, which is exactly the same. And it has its own environment and dependencies and packages in it. So you're not going to have where one of your application servers has a slightly different dependency than any of your others. Okay, so all right, so we have, I don't remember how we got here. So 12-factor pattern. Okay, so what we need to do is our runtime configuration. How do we configure our applications to be different from the staging? So maybe in staging, you're connecting to a staging database or different backing services that are in their staging environment. And now we're going to move that application into production, and it needs different config. We have immutable images, so we're not going to add something or change something on that image, but we still need to inject configuration information into that container. The 12-factor pattern way, the way Docker encourages, and it really is a good idea, is to use environment variables. I found that some teams have a little surprise or resistance around this idea. It can be, do I have to type export each one of my environment variables into my shell each time I want to run the app? No, just put all those things in a shell script so you can source it easily. With Docker, we're going to cover a Docker Compose file, which is the place where it's a YAML file where you can put all the environment variables and they'll be automatically injected into the environment. So no, it's not hard. Yes, you can see what's in your environment. If you run, so let's run that shells. Okay, so here's our app, and if we're going to pass it an environment variable, let's say, call it message. Oh, we need a command we're running inside shell. All right. So env, every shell's got it, and you can see what environment variables are set within your current shell. On the outside, when I did Docker run, I set an environment variable called message with a value of hello. And here you can see inside my container, I have that set. There's also some other things that happen to get set. We know what terminal we're on, version, where home's at, our local path, npm version. With the Docker run command, we can set multiple environment variables. Just keep repeating. So there it is, debug equals 1, message equals hello. So we can set environment variables that way for each run. So if you want to run 3 copies of your app on your local dev machine, each with different configuration, you just pass them different environment variables. There are a variety of advantages with this. Every modern mainstream or even sort of mainstream language has a good way to access environment variables. It is fast. It is simple. That makes it consistent across all of your code bases and all of your different languages. It's also there for every thread or process that your application starts. So it's there, it's handy, it's consistent, it's simple. Another point of objection is that people often have very large configuration files, and they don't really want to stick, hundreds of lines into environment variables. That makes total sense. One pattern that is handy is to simply specify a switch. So here I set debug true. Maybe that turns on or off 20 or 30 settings within your application code base. That's entirely acceptable. Another thing is that really here in this configuration, you're only going to want to expose things that you expect to change between different environments. So that doesn't have to be every configuration that your app supports. A lot of that configuration is really very static. It's more code than it is configuration. So all the thing you need to put here in the environment variables is things that you expect to change between environments, and it's entirely reasonable for your application to have defaults. There is some things you would like to fail hard. So which things you add defaults for and which things you require for a configuration environment variable to be present, it differs. But it's entirely fine to have your configuration that is not so much configuration, it just stays put to live in your code base, and then just to change the things that you're going to change, that from one environment to another. Also, this is a good place. Keep the secrets, different passwords, credentials, and the like out of your code base. Make that code base easier to share, and then just inject them at runtime. And one pattern that I typically use is to keep all of my Docker Compose files, so there's a Docker file that builds your image. A Docker Compose file is a file that you use to inject configuration, link containers together, and specify larger multi-container setups. I'll usually keep those Docker Compose files in a separate repository, often just call it ops, and then if need be, only the ops team can actually see what those secrets and other configurations for production are, because only they have access to the ops repository. All right. Keep close eye on time. All right, so let's cover a few other things that you could set. Let's actually run our little application here. So software-defined networking is something else I mentioned that you may want to, that's an advantage, and it's something we can configure at runtime, not prior to that. So we're going to, -P is we're going to do some ports. So we're going to port forward 8080 on the outside. Actually, let's do something different. Let's port forward 3000 on the outside to 8080 on the inside of the container. So there what I'm doing is just saying that, on the Docker engine, which is local one, runs on a host I have DNS set up for called dev. So right now, before I run the container and I try and hit port 3000, there's nothing there. Let's go up here. We're going to push the command for npm start, which is going to start our little application. All right, so so we can see here that our application started. It's running on, it's listening to on every interface at port 8080. I'm going to hit it with curl at port 3000 and get back a message. So what I did there was that I used the software-defined networking to say on that host, on port 3000, send all of those requests to this container and send them to its internal port 8080. You can open as many ports as you want, that no one else is using and that are within the 65,535 that each IP address is allowed. You can configure, you can pipe as many of those ports through to whatever you want. So if you're developing a web app and it's maybe nice just to have it at port 80 on your dev box, you no longer have to have root or IP chains or anything fancy. You just say, set it to 80 on the outside and 8080 on the inside, or 3000 or 9000, whatever you use on the inside of that container. Here we can see another convention. So this app accepts a variety of configuration options, and we can go have a look at how. Let's look at how Node.js accesses its environment variables. So something we have here. Okay, so in Node, process.env is how we access environment variables. I'm just renaming that to env so it's easier to access. Here I'm going to set up my database configuration. So I have env Postgres host, Postgres user, password, Postgres database. And here in our message, we're going to say, environment.message is what we're going to send back. Okay, so if we go back here, when we ran the app, we gave a value for message, and then we made a curl request to the application and got back hello with our message from the environment variable. We also logged to standard out the configuration for the database. And I did that to show that the configuration is unset and also to show locking. Another one of the 12-factor principles is log to standard out. So the 12-factor stuff, just log to standard out, and it's something else's job to collect those logs for you. Docker makes this a lot easier. Docker will collect those logs for you, and we'll go over it a little later, but there's a bunch of different logging engines, and you can have Docker just gather your container logs and chuck them where you'd like. So no more rotating log files, no more guessing where the log file is at, and it makes it very easy while we're debugging to see what's going on. All right. So back to the presentation. Okay, so environment variables, it is a good idea. Software-defined networking, the very basics. We're going to pipe some ports around. Okay, good idea. That does quickly become more than what we want. That's starting to get a longish command line. We don't want to make it longer and longer and then try and pass it around between everyone. We want all of our configuration to be in our repository somewhere. So what we're going to do is move on to Docker Compose. Let's go up a level in the abstraction and up a level in our power. One minor point before we go on, you don't have to specify the outside and inside ports that we're giving. We can just use another flag, and that will map whatever internal ports the application declares, opens, to some random high-numbered external port, and then we can use Docker PS to see what that is and connect to it in this case. But those are just randomly assigned. So probably not want to do that much, but it is available. And then just like the environment variable config environment variable, we can just repeat -e and keep passing more environment variables. We can repeat -p and keep adding different ports. We'll also touch on it shortly. There is an idea of volumes, which is doing the same thing but to file systems, and we can mount multiple file systems. We'll get there in a few minutes. All right, so we've got too many command line arguments to remember. So now what? Docker Compose. So Docker Compose file is a configuration file. Its language that it uses is YAML, yet another markup language. YAML is very easy to learn. It's just JSON without the curly braces. It is technically a superset. It can express a few things that JSON can't, but we're not going to use any of those that I can think of right off. So it's also any YAML parser can parse all of JSON. So if your team really doesn't like the idea of adding one more configuration language, it's completely fine to, pardon me, it's completely fine just to use a Docker Compose file written in JSON. Other people just look at you a little weird. So here's, as a demonstration, here's a one-liner that will convert. Let's make that. Make it actually go on one line. Okay. And we need to go. Oh, we're in the wrong directory. Example, sample app. And so this is a Python one-liner that is going to convert. Let's actually show you the file first. So there is the YAML version. I'll use that one-liner or anything else like it to convert it to JSON. Docker Compose really doesn't care, just as long as the file's there. And by default, it looks for a file named docker-compose.yml. You can stick JSON in there instead of YAML, and it'll be just fine. You can also rename that file to whatever you want, and then just tell Docker Compose where to look for it at. So we're going to look at the YAML version, though, just a little bit simpler to edit. All right. Okay. Now, if you are looking at Docker Compose tutorials online, the file format was not initially versioned, and now it is. So a lot of those tutorials may be referring to Docker Compose version 1.0, and they don't know it because there wasn't versions, but you don't want that. You want version 2.0. So just make sure that the Docker Compose files that you're looking at in the wild, the tutorials, look for ones that are Docker Compose. Yeah. Docker Compose version 2. All right. So what we need to cover. So the first thing is we're going to specify the version, Docker version, version 2. Then by tradition, we're going to place services at the top and other things. Here we're going to do volumes and networks at the bottom. Doesn't actually matter. Now look at the service block. So this service block is this. Handy thing with YAML is that white space doesn't matter, and that white space is significant, but extra white space lines don't matter. And we have commenting syntax there, the hash. All right, that first block that I've highlighted is our first service that we're going to define, and we're going to say build, and then that dot is for here. So this Docker Compose file is inside the sample app directory, so it will build that Docker file that we looked at earlier. So when this service starts up, if we don't already have an image, we will build it. Instead of build, it's fine to put an image name in there. Command is entirely optional. Maybe you can include the command in your Docker file, but if not, here's probably even a better place to stick it. Volumes. So we haven't covered volumes yet, and I want to observe our time as trying to keep to about 2 hours. Okay, move things along. Volumes are Docker's way of letting you have control over file systems. So the way you're going to get during development time, the way you are most likely going to get your code from your host into your container is you'll mount a volume that has your code in it that you're developing on your host, and you'll mount it inside the volume at whatever file system location you want. So here, we're using volumes to say everything that's right here, // we're going to mount it inside the container at /app. So if you'll remember from the Docker file that we use, that's where we stick everything anyway. That's what we're going to have when we get to testing and prod. We're just mounting stuff from the host right into that running container. Not messing with the image. It'll overwrite anything in that location in the image. But that lets us put our development stuff we're working on with our editor external to the container inside the container. Volumes are not layered. So it's common if you're going to have a large amount of data, say this is a database container, to put your database files on a volume and declare that volume when you're making the Docker file, or here at runtime using a Docker Compose file, or on the command line, just however you want to do it, so that they're not versioned. That's just for efficiency. Of course, if you want them versioned, well, hey, you've got a layered file system. You can also mount different kinds of file systems. So if you were using a clustering tool such as Kubernetes, maybe, and you're running on AWS, maybe you have a particularly fast shared file system, something, I'm blanking on AWS's term, but one of their faster network storages, and you want to mount it in as a file system, you can do that. So volumes, volumes are more difficult to manage in production, simply because we assume that disk access will be fast and make assumptions about whether or not other processes will be using it, and we want this to seamlessly scale to multiple machines. So there's just complexity that comes around that, but they're definitely there. They work well. I generally keep your apps as stateless as possible, avoid the need for volumes in production, but they work really well where we're moving the code we're working on into our container to run. We're also specifying the port, so we're going to attach to port 80 and on the outside. Easy way to remember this is everything on the left is on the outside, everything on the right is on the inside. That's the same for volume, same for ports, same for environment variables, just all the way along. So environment variables, we're setting a Postgres password, user, database, host. We're setting a debug variable, a message variable, and those are setting on inside the container. And then we've created a volume that are we showing it? No, we're not. We're just using it in one place. But you can declare volumes down here at the bottom, and then we could share them between multiple containers. We're also declaring a network that we're going to share between containers. So that's all that's required to define a network, and we can have as many networks as we want, named whatever we want, and we can specify different backing technologies here. But we just want the default Docker tech. We're going to call this network main. We're going to put both of our containers, both the one that's here, which is going to run a Postgres container using that image, Postgres 9.6 from the registry. We're going to run both of these on the same network, on the same machine, and away they're going to go. So, in case you didn't catch that, no more installing Postgres locally on your machine, trying to figure out which version you need for which app you're working on. It's just in the compose file. Done. All right, let's go start this up. So I mentioned some of the tooling that comes with Docker. So we've seen Docker Engine, the daemon. We've seen Docker CLI, the command line. The next tool you're probably going to want is Docker Compose, and it is for running multi-container setups. By default, it's going to look at that docker-compose.yaml file. We're going to tell it to come up. It's going to build the images. Looks like it's building npm and building our application image again. We gave our image an arbitrary name, that demo-sample app. That's why it doesn't see it. So it built as a fresh one, pulled down Postgres. Here, both of those applications are dumping their logs to standard out. So we can see them, we get some nice pretty colors. And our application is up. Curl at dev, just 80, so we can leave it off. And here we can see we've logged those environment variables that were set in the compose file, all right there. And those happen to be what the database needs for our application to connect. Postgres, our code, sharing data from sharing our code from the outside to the inside. Everything's set up, and it's just Docker Compose up. Okay, let's look at our next. All right, we covered V1 versus V2, multi-container setups, external networking. So, okay, we'll look at some more sophisticated Docker Compose files in a few minutes, I think. Let's go. So external networking links, that same pattern, stuff on the outside on the left, stuff on the inside on the right. Just wire things through as much as you need. Inter-container networking. Now it's time to go look at some of the fancier stuff. Let's see how we're doing on slides remaining. Volumes. Okay, we're doing okay. All right, so inter-container networking. Simple version is you can use DNS. Docker will automatically assign DNS names and we can just use them. So let's look at a somewhat more sophisticated project. So here, let's go. So here's the examples. This is the repository that has the slides. I'm going to look at composed examples, except let's look first at networking diagram. All right, so this is our theoretical setup based on roughly based on a customer of mine. What we have is we have 3 environments. We have staging, we have customer 1, and customer 2. We're running somewhat modified versions of this web-based application. The web-based, let's actually see if we can zoom this in a bit. All right, so each one is going to need an application server. That application server needs to talk to something handling background processes, needs to talk to database, which happens to be on RDS. It also needs image processing. So we do dynamic image, just image filters, scaling, cropping, sharpening, identifying key points in the image, live dynamically at display time. Those images are going to live in S3, so we have as much file storage as we want. We're going to store them using CloudFront so that they come in fast. So that's the basic setup, but we don't need just one. We need one for our staging and testing environments and such as needed. And then we have 2 customers. One we're going to call KSL and another Bobo Sales. So that is the conceptual diagram. For practical reasons, we have simplified it a little bit. And basically just combining things, we're going to have a single image service, single CloudFront, S3 file storage. We still need our 3 application servers, 3 background processing units, because they each run different. The background processing is part of our application, so its code is dependent upon the application server code, shared code base there. And then they're all going to talk to a single RDS database, database server that has different databases on it. So somewhat simplified. Let's go look at what, that's not an overly complicated networking diagram. It's not the simplest one you've probably ever seen either. So there's a little bit going on here. Let's see what that'll take to do. Let's jump over to the example. So this is in the Compose example folder. We will look at Docker Compose and scale this up a little bit. All right, so this Docker Compose file is somewhat, it's longer. There's no additional concepts here. It's just a little bit bigger. So we name each of our services. Here we have public sales. Our background processing is just handled by cron. So we have a container that runs cron. We have our image processing service. So this image processing service uses an open source project called Thumbore. Here's thumbore.net. Oh, not that one. All right. Here we go. Thumbore is an open source image processing server. It's quite advanced. It can do feature recognition, does a variety of optimizations for each client, etc., etc. It's written in Python. One of Python's interesting parts is that it has a global application lock. So if we want to make this scalable, we're going to need to run more than a single thread. So these blocks here are running are running 3 Thumbore services. We just happen to name them Thumbore 1, 2, and 3. Not very creative, but it works. And then putting them behind an Nginx proxy here in the front. So that is our image service. We're going to run this whole thing on a single host. So we have a proxy here that proxies between whether we're going to KSL or Bobo Sales or staging or making a request to the image processing service. So not sure what all we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 service blocks. Each one, we're passing it telling it the command, telling it the image, telling it environment variables, replacing them all in the same network. We're doing some proxying between them, and it's just all there. I'd like to point out this is production config, so we have restart always. So that is if your container dies for any reason, we'll just restart from a fresh image. It's also possible in the latest version of Docker to restart Docker without restarting your containers. So if you need to do a Docker upgrade, it's at least possible, just barely. Now we got that version out, and there's still a few caveats. But even if you need to upgrade Docker, that doesn't mean you need to shut down your containers. We have a volume that we're sharing. We call it cache, and we actually mount that volume into several different containers. And you can really do some fancy stuff here if you want. You can map that, we're sharing this one, we're mounting it to multiple containers, but our applications are aware that other people may be accessing the file system. You can map it into different places on different containers. You can map volumes into other volumes on the same or other containers. So really, you do have power to do whatever you want there. With networking, again, for this application, we're fine. Everything can talk to each other. We actually want most of them to be talking to each other. So we have a single network called main. We're going to stick everything on it, and we're done. Now, for this particular image, see how many times we use ports. So we actually only use the option ports once. And that here is we're mapping something on an outside port to an inside port. And what we're doing is basically have a front reverse proxy powered by Nginx that's going to handle all external requests into this network configuration. So it's just, for this application, it's just port 80. That's it. But how are my containers talking to each other? Let's look. So what they're using, so here, another convention, just have a folder called Docker files, and each one have your config for different services. Let's look at the proxy, and okay. Actually, let's look at the, I think it's more descriptive if we look at the Thumbboard service. Look at its proxy. So let's look at that one. And okay, so we named those Thumbboard instances, Thumbboard 1, 2, and 3. So here in the Nginx config, we're just telling Nginx to look at host, Thumbboard 1, 2, and 3. That DNS will be resolvable inside the container, and it just works. Okay, so that if you've had to set up software-defined networking before, that probably looks almost too easy. We happen to know that all of those services are on port 808080, and notice that I reused that port even though for this particular config, everything is going to run on the same host. Each one of those services is going to have, each of those containers will have an internal IP address, so it can have its full port range, and we're going to use DNS to know where they're at, and it just works. Yes, there are more sophisticated solutions for larger clustered applications, large production setups, but don't use them until you need them. They work well too. So here it is, voila. All right, let's go back to our slides. Inter-container networking, we've done. Volumes, all right, we've covered volumes briefly. Yeah, same setup, the outside-inside mapping, and production time usage, everything else. Let's check our time, and we'll see to what depth we'll go. Okay, doing good. Okay, so logging. Logging is something we mentioned briefly before. So logging the Docker engine has a variety of logging drivers. You can swap them out. More being added. You can write your own. By default, it's JSON file, which just means all the logs that your containers spit out to standard out are gathered up and stuck in a JSON file on disk. And the Docker engine can then play them back to you. You can see them for a specific container, for a group of containers, as you like. But we also have, we can stick to the host syslog, to journald, AWS logs, Google Compute Engine. If you're using ELK and Elastic and Elk Stack, Elasticsearch, Logstash, and Kibana, or otherwise a Logstash or FluentD setup, we can just direct the logs directly over there. So it's part of those 12-factor patterns. Don't build log handling into each one of your applications. Just have a separate tool that does that. This makes it easier. Docker stats this is a handy command. So let's actually look a little bit. We'll do it here first. So Docker stats. I probably didn't tell it which host. Come on. There we go. Okay, so this is looking at the container that I'm running locally, the setup that we just started in the shell that's above. We have those two applications running. One of them is Postgres. One of them is our little Node.js server. So we have two containers, and Docker stats. It just gives me a streaming somewhere output to it from a few Linux tools, but top would give you so we can see what we're doing. So this is going to be pretty static because we're not doing much, but we do know percentage of CPU each container is using, container ID, memory usage, percent of the total memory, network I/O, in and out, block I/O, in read and write, in and out, and its PIDs. So it's just a simple way to see some basic stats. What containers am I running? What's going on? So this one isn't too informative, and that container is not too far away. But let's look. I'll actually go ahead and kill that one. Close one of our terminals. I mentioned before and a few times throughout that Docker is a client-server model. So the Docker engine can be running wherever, and your Docker client can be running wherever, and they have their own protocol and authentication. But if they can talk to each other, then we can see some stuff. So let's actually do. So I guess what I'm doing here we'll cover in a second. But first, let's just continue with Docker stats. So what I just did was I set some environment variables to tell my local Docker command line to talk to a remote Docker server. And we're having a little bit of issue with network connections. So we may not be able to demo. But what we would have seen is the same as the Docker stats locally. It'll show every container on that host and its I/O, network, disk, memory utilization, and it will stream updates to those stats live from that host. And that host, I would say we have network problems. That host happens to be on AWS EC2. And I get the stats locally, just that handy. Fancier monitoring. So let's switch back to my local machine, and so we'll bring up that brought up our two containers. Now we're going to run. Okay, so we didn't have this container, Google cAdvisor locally. So here I told it to run, but we don't have the image, so it's pulling the image down for me. And it'll just do it and set it up. Then let's go hit, what port do we forward it through? 8080. So as you scale up, different clustering technologies, Kubernetes, DCOS, AWS Container Service, etc., they all have their own different dashboards, but this is more for the small end of things. It's a handy image produced by, it's an application but it's for Docker, so it's always distributed as an image called cAdvisor from Google. And here is just your basic, I'd like to have a simple GUI that tells me what's going on. So here we can see, so CPU, shares, allowed cores, memory, total memory in the virtual machine. We get a few dials about how much CPU, memory, file system we're using, the processes that we're running, and these are for those 2 containers on my local machine. We get some graphs, our CPU utilization, 0.05, usage per core, usage breakdown, memory, network. So we get some simple graphs, time-based. They're pushing to the client. You can see as they move. We can also get that's for everything. Let's click on Docker containers. Let's click C, a subcontainer. Let's look at what Postgres is doing. Very little CPU, very little memory, very little file system. It really doesn't take much to just run a container. Network errors, all of it. All right, so cAdvisor. It's a very simple way just to run simple stats. All right, let's cover a few other things. One tool that you have seen me use a few times, but I haven't explained yet, is Docker Machine. So Docker Machine is a handy tool for provisioning. If you're new to ops, provisioning is the step where we go from we have nothing to we have machines. Configuration is the next step, where we take a newly existing machine or resource, a load balancer, and configure it as an environment for our application. Docker Machine handles the create instances, and it just works with machines. So what this can do is, if I want a machine running Docker Engine on DigitalOcean, then I just say Docker Machine create, give it the DigitalOcean driver, give it my credentials, or set my credentials in the environment variable, in environment variables that it looks at, and a minute or so later, I'll have a VM running on DigitalOcean with Docker Machine installed, ready to connect my local Docker command line to. Docker Machine has a variety of drivers, so AWS EC2, DigitalOcean, Rackspace. I think there might be one for Linode, Exascale. I'm trying to think. There's also ones for local, so for VMware. If your company is running on a VMware cluster, got you covered. There's ones for Parallels, Fusion, and VirtualBox, so you can provision local development machines with. And then besides just provisioning them and getting Docker Engine set up and working well, Docker Machine also lets you manage the connections between them and manage those machines. So here we can see that I have set up short names, but I have I have 4 client machines that my laptop knows about, and then my dev, so BF5, Bobo, Dev, Grey Day Dairy, and URSport FB. 4 of these are running on Amazon EC2. Their state is up. I have their IPs that I can connect to. I know which Docker version they're running, if they've had any errors recently. Here's that little asterisk letting me know that the one I'm currently have environment variable set for is the dev machine, which is my local dev one. And the command that I've been running for a bit, eval that is setting, and I use a slightly different shell. If it's in bash, we would be using the backticks for eval, but my shell uses the word eval. So if we do it without the eval, we can see what Docker Machine is giving us. So Docker Machine v and a name produces the shell snippet that will be needed to set the environment variables so that your local Docker binary can connect to that instance of the Docker machine. And it's smart about it detects which shell you're using and spits out the correct syntax for that. So we start a fresh shell, and env, and we'll grep Docker. there's not much there. But if I do eval that and then grab my environment, oh, they're set. And now I can dock to that Docker engine. So this is a really handy way to very quickly bring up or tear down machines on different cloud providers or locally, have Docker engine installed on those, and then switch between them so that you can keep all of your Docker Compose files, configurations locally on your machine, and just use Docker Machine to provision hosts, switch between which one, and bring up services on them as you like. That really does scale quite well up to a couple machines. Beyond that, we're wanting to probably use some different technology, and we'll cover that shortly. You can throw away SSH access on your servers because you don't have to do anything to the server except have Docker engine running, and you talk to the Docker engine like this because all you'd ever want to do is tell containers to run, start and stop, and maybe where to stick their logs, which is all defined in Docker Compose files, which are very small and are in your repository and are versioned. So, yes, if you know DevOps, you're saying, "Hooray! That cuts down so much work." If you don't, you're maybe saying, "Oh, we can do that." And yes, that is the way it should work. Okay, so now we move on gently to what does this mean? So what does it mean for application architecture? The first thing it does is it enables a microservices design. If you have tried to do microservices and found it to be a miserable experience, wondered what all the hype was, it may have been because without containers, without a solution like Docker, microservices are extremely hard to manage effectively. It really does enable microservices to be a tool instead of what amounts to being a way to shoot yourself in the foot. Sort of along the same line is add-on services. So at my company, one of the technologies we very much embrace is PostgreSQL, the database. And Postgres is a very capable database. One thing that we would like to have is a RESTful API for the database, similar to what Mongo or CouchDB, Elasticsearch provide. So there happens to be a project written in Haskell, very fast. It inspects your database schema and then serves up requests. You can set an ACL and the other things you need. So we often want to run Postgres with that. It's called PostREST, that API project that I mentioned. We want to run them together and just, as a thing. This is the thing we're going to talk to now. And adding that add-on RESTful API service to our project is now about 6 lines of YAML in our Docker Compose file. And our PostgreSQL database has a RESTful API, and that's all there is to manage. Maybe your applications would go faster if they used a HTTP cache, such as Varnish. But to do that, prior to containers, well, you need to get ops to do it. They need to add it to their configuration management software. They might need to provision a host. There's just a lot more complexity there. But if we want to compose together a variety of open source applications, we can. Check our time again. All right, coming up on the end. So the image service, Thumbboard, that we described. So if you're building a PHP application, you've probably written code to handle images provided by users, to upload them to the server, possibly crop and resize them, maybe to detect feature detection, to know which part of the image to suggest should be cropped or is important, maybe some filtering to enhance the images. You can build that all into your application. Nowadays, with a good framework and a few good libraries, you can probably build that into your application without a week's worth of effort to do it well. It depends on the size of the project, whether it's a day, a week, or a few months. But there's all this chunk. There's code you had to write, framework code, needing to leverage your framework, needing the libraries, needing the dependency resolution, and then really we've just combined, mixed up, handling a scalable image service with your application. So now if we need more image handling capacity, we have to scale your entire application, not just the image handling ability. Here with microservices, which are now something within reach really with Docker, that Thunborg service can be reused by multiple projects if needed, if desired, or not. It's just a few lines of configuration within YAML, in YAML in your Docker Compose file, and now we have a scalable image handling service that can back to S3, that's open source, that someone else is maintaining, that is very good, and it's just a RESTful service that we can now compose. So microservices done well, which Docker allows you to do, now lets you think not on the library level of what we can reuse, but actually on an interface or application level. There are applications that do a great deal of the things we need in our projects, and we can pick and choose scalable, focused solutions and use them. It's not magic, but it helps. Development. So once upon a time, a long time ago, I worked for a company that the standard procedure when a new developer joined the company was to pair them with one of the preferably most senior developer handy. It was expected that it would take them a week, and together they would set up the environment for doing the development. And it wasn't comic relief, but at the end of that usually took about a week, and the final step was to issue the command that started the application 3 times. For a variety of reasons, you did have to do it 3 times before it would work. So the saying was that it took 2 devs a week, and then chant the magical word 3 times at the end, and you had a new developer with a development environment. He could begin reading the documentation and starting to do some work. That is not an acceptable way to scale your team. One of the things that Docker and Docker Compose allows is that you don't have to care whether the new dev is running Windows or Linux or Mac. You don't have to help them get backing services, Elasticsearch cluster or your Postgres or whatever set up. You don't have to care that we use this particular version of a binary and we configure it in an odd place, and they need to go in and modify their host in such and such a way. It is just Docker Compose up. Simply standardize on that and let every project, every developer always run the code the same way. We don't care about the host. All the configuration, all the backing service setup is in Docker Compose. Configuration of those services is in their own Docker Compose file. It saves a lot of time when you're switching developers between teams, onboarding new developers. It's nice. What does Ops get? Ops gets the ability to provide an actual platform to dev. So rather than taking emails or a ticketing system, they can use Docker and its APIs to provide raw, reliable, managed, with all the monitoring and alerting around it, compute, storage, networking that dev needs. You can provide immutable infrastructure. If say you're running a deploy and it goes wrong, then you can throw away the new stuff and go back to the old because you didn't modify the old. It is immutable, you still have it. This is a wonderful video from Martin Fowler. It's about 15 minutes long. It's all about infrastructure as code and the idea of a Phoenix server. So a lot of people are deploying Snowflake servers. They're unique, they're one of a kind, they've been set up by SSH, or maybe if we're lucky, our configuration management software. And we try for consistency, but we don't actually know everything that's on that server, and we're careful of those servers because we don't know if we can ever get one back that's just like that and that'll actually run our app. A Phoenix server is the other end of the spectrum. Phoenix server is burn it down and it starts again exactly the same. Burn it down again, starts exactly the same. And then in your ops, rather than being afraid of burning it down, it can be customary that every deploy, and maybe you're deploying continuously, so this is 6 times a day. You can burn down all the configuration. You can destroy the VMs if you want. If you're running Docker inside a VM on EC2, if you're on bare metal, it's probably just the containers. But you can burn everything down and start it fresh. And you're doing that so often that you're confident that you can do it anytime you want. Another thing that this enables is canary releases. So canary in a coal mine, if you have a release that you believe is solid, it's what I mentioned before, where you can roll it out. If for some reason it's not working, you can go back because you do have the previous version. You did not go out and mutate your servers, change some configuration, install some other dependency, and we don't know how to get back to the previous version. It's just, here, on half the application servers, we're on the new version. Let me check all the logs. Okay, they're happy. Let's bring them all up. Or they're not happy, let's take everything back. We have the previous exact byte for byte environment and binary in the Docker file ready to go. All right, so you got all this working. What's next? So there's a different set of tools, whether you're working in dev, whether you're working in small scale production, medium scale production, or a seriously large scale production. The general progression is that Docker Compose works fine so long as everything runs on a single machine, and you can get by as long as everything runs on a few machines, say 3 or less, maybe 5. Docker Compose is a great way to define those services define the containers within a service. It would be possible to have maybe each service running on a machine with its own Docker Compose file, and they know how to talk to each other. But it gets rough when you start scaling to multiple machines with just Docker Compose. Docker Swarm is the next tooling up. Docker Swarm allows you to present a collection of machines as a single Docker host, which again puts them back in the terrain of being able to easily set up with a single Docker Compose file. Docker Swarm, I think Docker is testing it on hundreds, perhaps thousands of machine-sized clusters. I would recommend it more for maybe a max of 20 machines clustered together. Somewhere in the 10, 12 machines clustered together, it's probably more of its sweet spot. So if you've outgrown just Docker Compose, use Docker Swarm to present a collection of machines as a single Docker host, still use your Compose files, and all's happy again. So probably the majority, yes, there are much bigger apps that would never run on that size of infrastructure, but I found for a lot of teams, a lot of projects, a couple of machines, particularly if you make them a couple of big machines clustered together, really is a nice solution. If you're going to go beyond that, say somewhere between the 12, 20 machine plus to thousands of machines, what you want is a proper clustered Docker setup. One of the most popular ones at the moment, it really is a rather amazing project, is Kubernetes. It's backed by Google, Red Hat, Canonical, I forget who all is very actively participating. They're very open to the community. It is it runs on any cloud infrastructure or bare metal. They have pre-made setups for AWS, Google Compute Engine, Rackspace, Exascale, etc. It provides, there's a graphical dashboard, there's a system, you can see what you're doing. It has additional concepts that you'll need to learn that help you make optimal use. There's a scheduler to schedule which host your jobs are on. There's the idea of a pod and a service to help keep containers that need to communicate very intensely close together on network and machines. There's a variety of additional patterns that you'll want to cover. But it really does produce a very nice clustering machine. Some of the success stories are having one DevOps person per 100,000 containers, or possibly per million containers. So this really does give you a lot of leverage. Kubernetes does come alerting included, monitoring included, logging included. Swap them out with whatever's provided by the cloud service you're on, or provided by best-of-breed open source tools. Plug and play its own API. It's also quite sophisticated. It's a very good use of artificial intelligence. One of the lead engineers has a background in robotics, and some of the things that Kubernetes can do is observe the state of your cluster, observe the desired state of your configuration, and if something is not right, make intelligent decisions to make the two converge. So you just change your configuration file so that you have more services and there's not enough hosts to run them on. Kubernetes scales those up. You have a service that keeps dying. Kubernetes can do some work to address that. You have hosts that are overloaded. Kubernetes can move stuff around, make them fit again. You have infrastructure that just disappeared. We don't know what happened to it. Amazon EC2 instances disappeared on you or something, and it will notice it, detect it, spin up new ones, and it will do the fastest thing possible to replace that infrastructure and restart those services on it, or possibly start those services on other hosts or spare capacity within the cluster, and just take care of it and tell you what it's trying to do. Very handy. One of my personal favorites at the moment is Triton, and it is the clustering technology behind Joyence Cloud, Joyence Container Service. It runs on Illumos. We get that additional level of security, and with a hosted Triton instances, it presents an entire data center as a single Docker host, and we can still control massive deployments with a simple Docker file. You can also run Triton on your own infrastructure. There are many more options: AWS Container Services, Mesos, DCOS, etc. All right, that concludes our presentation on Docker. If you're interested in DevOps development or consulting services or more information, please give us a contact. See our website at noyanlabs.com. Thank you. Bye.